Just starting with the basics here about energy, all right? All chemical reactions involve energy. Some need more energy, some use up energy, some give off energy, but energy is going to be a big part of it. And thermodynamics is the science study of energy transfer. And if it's applied to chemistry per se, then it would be considered sometimes thermochemistry. But if you call it thermodynamics or I call it thermodynamics, it's totally fine. It's the same thing. It's the study of energy exchange between what you start with and what you end with. So in the lower left-hand corner there, you've got some peanuts being burned. Peanuts actually give off energy, and it's enough energy to boil water, which is kind of cool. And we eat peanuts and other food items in order to get that energy into our body so we can do the things that we do. So it's very fundamental to life itself.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product favored.
So in that video, which is kind of fun to watch, by the way, we're dropping a gummy bear into molten potassium chlorate, KClO3. And my goodness, there's a lot of energy given off, and you can see all of that stuff happening, blah, blah, blah. I believe that this reaction manifests the reason why we eat gummy bears and other foods in general, because those foods hold a lot of energy inside them, and that's what makes us happen, makes us do our things, makes us move around, makes us learn chemistry things, make chemistry lectures, in my case, on a computer, whatever. It allows us to do what we need to do, okay? And the bigger the gummy bear, like in the upper left-hand corner there, the more energy is released. So this is the kind of thing we're going to study in this section. So that's called the gummy bear reaction. It's pretty fun to do. You can do it in the lab. If you're interested in doing this actually in the lab, let me know. So a question that a thermodynamicist will ask themselves is like, what drives chemical reactions? Why do some reactions happen? Why do some reactions not happen at all? Why do some reactions only happen under certain conditions? And that's a really valid question to ask when you're a chemist, definitely, no question. But it's also nice to know why reactions occur and also how fast they go, because we're humans, all right? We get impatient and stuff, and if the reaction is slow, it's like, oh, on the other hand, some reactions are so fast that we don't even think about it. So these are great questions that scientists should ask, and especially chemists. Now, the first question as to what drives chemical reactions, that answer is oftentimes obtained through thermodynamics, the study of energy transfer. But the second question as to why they occur and how fast, that question is going to be answered by kinetics. And kinetics is something we'll talk about this term too. In this chapter, we're going to start talking about thermodynamics, which is the energy exchange. And that's going to be a topic we'll talk about both in this class and in Chem 223. Kinetics is something, though, we won't talk about right now, but we will talk about later. So there's going to be some points where there's going to be like an answer, like the reaction will happen, or the reaction won't happen. And that's thermodynamics basically giving us those answers. But if you want to know how fast the reaction is, or how slow for that matter, that's going to be a question for kinetics. And we'll have to do separate things to figure that part out.
Thermodynamics determines whether or not a reaction is possible. A reaction that is not thermodynamically favored will not occur to an appreciable extent. Sand is not thermodynamically favored to change into elemental silicon and oxygen, and if undisturbed, no reaction will occur. Reactions that are favored both kinetically and thermodynamically do occur. Paper, for example, will burn quickly in air if ignited.
So we're seeing here two different kinds of reactions. And the first one there that it talked about was sand decomposing into silicon and oxygen. And sand is essentially a type of a silicate, which is something you'll talk about in geology. It's basically a silicon-oxygen combination of compounds. And in theory, there should be some way to extract the silicon and oxygen from the sand. But I'll tell you, it's not going to happen by default. It's just going to sit there and it's going to look at you, and you can wait for millions of years years, and it's still going to be sand. So sand is something that thermodynamically, nope, not going to happen. Thumbs down, all right? We don't have to ask if it's going to happen fast or slow or not, because thermodynamics says, nope, not going to happen. So that's one example. And there are a lot of reactions that just won't happen. Now, the second little video there showed a piece of paper burning, and that definitely will happen, all right? If you put a little spark on that piece of paper, it's gone, all right? So that's an example of thermodynamics saying, yes, this reaction will occur, all right? Now, the question of speed, you can see that reaction was pretty fast. So kinetics would predict that that reaction is fast. Some reactions will occur, but they're very, very slow. So thermodynamics is kind of an overall thumbs up or thumbs down. This is how I think about it. And it'll either say the reaction will occur or the reaction won't occur. But just because it will occur, you should also ask the kinetic question. Is it going to happen like in my lifetime? Will it happen, 3 centuries from now? What is the speed of the interaction? That's another interesting question to think about.
Kinetics controls the rate of a chemical reaction. Even if a reaction is thermodynamically favored, if it is not also kinetically favored, it will not occur in an observable timescale. Diamonds are thermodynamically favored to turn into graphite, but the reaction is so slow, it never occurs. Some reactions take more time than others. Iron nails react with oxygen slowly, producing rust over a period of months.
So here's 2 examples of reactions that will happen. Thermodynamics says, yes, these are both going to happen. And the iron nails going into rust shouldn't be a big surprise. You leave something outside in the rain, it starts to rust and stuff, no big deal. And it goes pretty quickly. That's something we can observe on our timeline. But one thing that may not be familiar to you is that thermodynamics says all diamonds are going to decompose into graphite. And diamonds, as you know, are worth a lot of money, all right? They're used in rings and jewelry and stuff like that. And graphite is the ingredient in pencils. So if you're writing notes with a pencil right now, you're using graphite. Graphite is cheap, right? So if, oh my gosh, all my diamonds are going to go into graphite, you might oh my gosh, I got to go sell all my diamonds really fast. But the thing is kinetics says that diamonds to graphite is super slow. As a matter of fact, all of your diamonds that you have right now, if you have any, all of them will be around for your children's children. All right. It's just a very, very slow process, and it shouldn't happen in your lifetime and even in your children's lifetime. So again, both the diamond going to graphite and the iron going to rust, those are both going to happen. But the kinetics of the rusting is relatively quick. The kinetics of diamond to graphite, very slow, but both of them get the thumbs up from the thermodynamic rules. So you can see the kind of stuff we're entering into. We'll first ask if the reaction can occur or not. So sand to silicon and oxygen, no. Paper burning, yes. All right. But the second thing we'll ask then, if it does occur, how fast, how slow is it going to be? Diamonds to graphite, incredibly slow, glacially slow. On the other hand, iron to rust, relatively fast. So these are the kind of questions we're going to start talking about in this section. So what makes a reaction happen? Like, why do thermodynamic rules sometimes say, yes, a reaction will occur, or no, a reaction won't occur? Well, there are some general patterns, and we'll develop this theory as we go through not only this class, but Chem 223. But when a reaction happens, that means that it's product favored, like the product is going to be favored over the reactants. And if you can form a precipitate, that usually is a good reason why it's product favored. So a precipitation reaction, those are all product favored. Also, if you form a gas, that's a product favored reaction. So we saw in the net ionics lab that if you make CO2, for example, from H2CO3, or you make NH3 from NH4OH, those are both examples of making a gas, and those are product favored too. And finally, you can also just make water. And I know water seems kind of trivial because we use it all the time, but in an acid-base reaction, that's exactly what happens. You get a lot of energy out when you make water, pretty important. So the precipitation, gas-forming reactions, and acid-base reactions that we've seen, all of those are product favored. Other examples of product-favored reaction include all the redox reactions. So if you have an electron transfer, those are product-favored. In general, reactions that transfer energy to the surroundings are product-favored. So what that means is you have some chemicals, the reactants, and somehow they're allowed to release energy into their outside environment, the surroundings. And generally, those are product favored. Now, a term I used earlier, and a term I'll use again here in a little bit, exothermic. Exothermic means that if you have a reaction, energy is released to the outside, and all of those are basically going to be product favored. Let's start talking about energy, and now we can predict if energy is transferred from the reactants to the outside. And there's two basic types of energy. They're called potential energy and kinetic energy, and they're both really important. Potential energy is generally the energy due to a position. So like, for example, in the picture in the upper right-hand corner, that's a bungee jumper. And that bungee jumper is at the top of a bridge or whatever, about ready to jump off. That person has a lot of potential energy because the minute they step off that little platform, whoosh, here they go. It's stored energy. Now, potential energy in chemistry is usually chemistry within a bond. So if you have an OH bond in water and you break it, that's going to have a lot of energy inside it too. Chemistry, in terms of potential energy, it's usually positive and negative particles being held on to each other. The electrostatic energy, those ionic bonds, a lot of energy inside them. Covalent bonds have energy too, don't get me wrong, but the ionic bonds are usually stronger. You can also have gravitational energy when two things are attracted. That's more for physics and chemistry, but it does sometimes apply. And nuclear chemistry, the power within the nucleus, is another form of potential energy. We'll talk about nuclear energy at the end of this quarter when we talk about radioactive chemistry. Kinetic energy is the energy of motion and of movement. And this is where things actually happen. So you take the potential energy, the stored energy, and you transform it into an energy of motion, essentially. There's three main forms of kinetic energy. First one is called translational. And in physics, this is an equation that's used. You don't have to worry about it. 1/2 mv squared. We saw this in the gas chapter as well when we're talking about how the energy of gas is the heavier atoms go slower and the lighter atoms go faster, blah, blah, blah. Anyway, it's not one we'll use a lot, but this is one version of it. So the bungee jumper definitely starts picking up his or her speed. This person's going to have a lot of translational energy. Vibrational energy is something you see in a molecule. So vibrations are intra bonds, like between the hydrogens, the white atoms, and the black carbon atoms. And they literally vibrate back and forth. And as long as you're above absolute zero, this is actually a type of an energy as well that takes place. And scientists, believe it or not, can actually measure vibrational energy. That's something you'll talk about in organic chemistry. Rotational energy is another form of energy, and it's when the whole molecule itself is like rotating around left, right, up, and down. So most of the time, molecules, like the little water molecule there in the lower right-hand corner, they experience all three types of these energies. First of all, they usually are moving somewhere to something, maybe an ion, who knows? That's the translational energy. And as they move, they're rotating around, all right? That's the rotational energy. And the OH bonds are actually vibrating. They're going back and forth, kind of like a dance. So that's vibrational energy. So a scientist, when they're thinking about the energy of these things, they have to think about all three types of energy. When it comes to energy, scientists like to think about both the system and the surroundings. And this is kind of an important concept too. So the system in a chemical reaction, it's usually the reactant molecules themselves. So in this particular piston there on the left-hand side, inside there's hydrogen and oxygen. So that would be the system. And probably in this type of reaction, the hydrogen and oxygen will combine to make water. So the system's like the active pieces, the parts of the chemical equation. But the surroundings are also important too, because all of these reactions, when they happen, will either give off energy or take energy. And the surroundings basically are the chemical species that affect it. So for example, if you're doing a reaction in solution, the solvent molecules would accept the energy that's given off, or they might give the energy if it takes energy. In that thermos down there, you have an isolated system. system so that thermos is isolated, the energy stays inside. And you can also have closed systems like the cup of hot soup with the lid, or open system when you take the lid off, all right? And all of these things are important for energy transfer. And again, in physics, you'll probably talk a lot more about that than we will here. But I just want to introduce these terms. System and surroundings is going to be important for us. And again, systems usually just the reactants that are forming some kind of products, and the surroundings could be solvent, it could be air, molecules around it, whatever, the metal that supports the contraption, who knows? But those are the things that will absorb energy or sometimes have to give up energy to make reactions happen. Thermal energy is a type of kinetic energy, and that's what we'll usually measure when we're talking about it. And thermal energy is related to the motions of atoms and molecules and ions, all that kind of stuff. In the lower right-hand corner, you see a hot liquid and a cold liquid, and hot liquids just move a lot faster than the cold liquids do. So hot liquids have more thermal energy and cold liquids have less thermal energy. So temperature is a way to measure something if it's hot or cold, and they're always relative expressions, because you might have things that are cold that are hot compared to something even colder, etc., etc. But the important thing to remember is that, boy, if you have something that's hot, you have faster moving molecules. It'll have a higher temperature, it'll have higher thermal energy. On the other hand, if you use your thermometer to measure something cold, then that will have slower moving molecules with less thermal energy inside them.